Welcome to the section on modeling. In this section, we shall start by looking at one of the first techniques which was employed in solving the problem of object detection, and that is the sliding windows technique. With the sliding windows, what we do is we break the input image into several grid cells. As you could see right here, we have this cell, this cell, this cell, this. So we have a 3x3 grid cell right here. Now, for this portion, or for the first grid cell, as you could see, we pass it through a conv net, and then subsequently through fully connected layers, and then we have the outputs which tell us whether there is an object in this cell or not. And if there's an object, the conv net tells us that it belongs to a particular class, and also it also gives us this bounding box. Now we slide to the next window or to the next grid cell, so hence the name sliding windows. We slide to the next, we slide to this, slide to this. At this point, we obviously see that we have objects. This we have an object, this we have an object, this we have, this we have, this we don't. So that's how this algorithm works. We basically slide through all this and then pass it into a conv net to deliver the required outputs. Now notice that here we're working with a 3x3 grid cell, but in practice we have something like this instead. Here we have a 14x14 grid cell, 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So this is a 14x14 grid cell, and for each of these small cells we actually pass it through this conv net. Now clearly we see already that this method is very computationally expensive. So even at training is expensive, but we're still at detection. So when we want to detect, or after training our model and we want to detect to see whether there's an object in the image or not, or to classify that object and also to locate the objects, we have to pass through each and every one of this. So if we have to imagine working with embedded systems, like for example in the self-driving cars, this becomes very complicated because it's going to take much time to slide through all of this and then pass through a conv net. And because of this problem, single stage detectors were developed where we don't have to actually do this. We don't have to pass through or slide through each of these cells. All we do is we pass the image into one conv net, and then we get the outputs immediately, such that when working in low resource systems, object detection can be made possible. The next model we shall be working with is the very popular YOLO model, which actually stands for You Only Look Once. That's Unified Real-Time Object Detection, by Joseph Redmond, Ross Gilshik, Santosh Divala, and Ali Farhadi. And this was developed in 2015. Here the authors present YOLO as a new approach to object detection. So prior work that's worked before this on object detection repurposes classifiers to perform detection. Instead, they frame object detection as a regression problem to specially separated bounding boxes and associated class probabilities. We shall get into this once we get deep into the paper. A single neural network predicts bounding boxes and class probabilities directly from the full images in one evaluation. So this is a one pass or a single stage detection model. Now, since the whole detection pipeline is a single network, it can be optimized end to end directly on detection performance. Now, one great point about this architecture is that it's extremely fast. The base YOLO model processes images in real time at 45 frames per second. A smaller version of the network that has a fast YOLO processes an outstanding 155 frames per second while still achieving double the MAP. Now the MAP here is actually the performance metric for object detection systems. Now, compared to state-of-art detection systems, YOLO makes more localization errors, but is far less likely to predict false detections where nothing exists. Now, the YOLO learns very general representations of objects. It outperforms all other detection methods, including the deformable parts models and the RCNNs, by a wide margin when generalizing from natural images to artwork on both the Picasso dataset and the people art dataset. For introduction, humans glance at an image and instantly know what objects are in the image, where they are, and how they interact. The human visual system is fast and accurate, allowing us to perform complex tasks like driving with little conscious thought. Fast, accurate algorithms for object detection will allow computers to drive cars in any weather without specialized sensors, enable assistive devices to convey real-time scene information to human users, and unlock the potential for general-purpose, responsive robotic systems. Now, the current detection systems repurpose classifiers to perform detection. So basically, they're using the convolutional classifiers or the conv layers or the conv nets we're used to working with already when dealing with classification models. To detect an object, these systems take a classifier for that object and evaluate it at various locations and scales in a test image. So basically, this is describing what we just saw or what we just looked at in the slides with the sliding windows. Systems like the deformable parts models use a sliding window approach where the classifiers run at evenly spaced locations over the entire image. So we've seen that already. Now, more recent approaches like the RCNN, this is another very popular approach which is used up to today. So more recent approaches like the RCNN use region proposal methods to first generate potential bounding boxes in an image and then run a classifier on these proposed boxes. So unlike the YOLO, that's this you look only once, which is single stage, that is, we just take an image, we pass it through the model, and then we have our output. With the RCNN, we actually have to pass it through a first model which extracts or proposes regions which it thinks will contain objects, and then after we have a classifier which now then tells us where exactly these objects are found, what classes they belong to, and actually if at all there is an object or not in that part of the image. So after classification, post-processing is used to refine the bounding box, eliminate duplicate detections, and rescore the box based on other objects in the scene. These complex pipelines like that of the RCNN are slow, are hard to optimize because each individual component must be trained separately. We reframe object detection as a single regression problem. So what has been done previously wasn't end-to-end, but now we have the YOLO, which is coming as a single stage end-to-end object detection system where we could input or we could have some images as input, we have the outputs, and then we just train the model without having to do any pre-processing as compared to the RCNNs. But it should be noted that the RCNNs have evolved today and we have faster RCNNs. Now, they reframe the object detection as a single regression problem. We've seen this already. Now, YOLO is a referentially simple, as you could see in figure 1. So let's go to figure 1. We have, okay, this figure 1. So let's zoom this. As you could see right here, we resize the image. We run a convolutional network. So basically, this is the image. We run a convolutional network and then non-max suppression to have this kind of output. Now we shall look at non-max suppression shortly. So that's it. And then we could see that this unified model has several benefits over traditional methods of object detection. First, YOLO is extremely fast, which is very important in real life because if you have a very high accuracy model or system and that it can't be used in practice, then it's actually useless. So it's important that when modeling an object detection system, we have to take into consideration the speed. So since we frame detection as a regression problem, we don't need a complex pipeline. We simply run our neural network on a new image at test. Now this base network runs at 45 frames per second. So this means that if we're having a real-time video of 30 frames per second, then the YOLO actually does object detection faster than real time. And in that sense, we could do object detection on a real-time video feed without any abstractions. So right here we have this on the it should be noted that this is on the Titan X GPU. So this obviously is going to be reduced if we were dealing with a low-end GPU or a CPU. And the fast version, that's a lighter version, runs at more than 150 frames per second. This means we can process streaming video in real time with less than 25 milliseconds of latency. Furthermore, YOLO achieves more than twice the mean average precision, that's the MAP, of other real-time systems. So for a demo, you could click on this and you view that. Second, YOLO reasons globally about the image. So apart from the speed, YOLO reasons globally. So unlike the sliding window and region proposal based techniques, that's like the RCNN, YOLO sees the entire image during training and test time, so it encodes contextual information about classes as well as their appearance. So actually what it does is it encodes information about the classes, about their location, and about whether it's an object or not in just one convnet, instead of having to divide this into several different convnets and several different subsystems. Fast RCNN, which is a top detection method, mistakes background patches in an image for objects because it can't see the larger context, whereas YOLO makes less than half the number of background errors compared to fast RCNN. Then thirdly, YOLO learns generalizable representations of objects. When trained on natural images and tested on artwork, YOLO outperforms top detection models like the DPM and RCNNs. So while these RCNNs are sometimes achieving a higher MAP, that's mean average precision, we notice that it happens that these systems actually overfit, as when we switch now to this artwork data sets, YOLO outperforms all of them. So this tells us that YOLO is less prone to overfitting. Now, since YOLO is highly generalizable, it's less likely to break down when applied to new domains. So that's a point or unexpected input. Now, the system divides the input image into a S by S grid. So like as you could see right here, we have this S by S grid where S equals 7. So we have a 7 by 7 grid. You could see it better right here. So this is the image which has been divided into that 7 by 7 grid. And then each grid cell predicts B bounding boxes, that is, it tells you exactly where the object is found in the image and the confidence scores for those boxes. Now the confidence score is actually a reflection of how confident the model is that the box contains an object, and also how accurate it thinks the box is that it predicts. And this confidence is actually defined as the probability of having an object times the IOU of the truth with the predicted information. Now we shall look at the IOUs to better understand this formula. Before looking at that, we should also note that if no object exists, then this confidence score should be 0. Otherwise, we want the confidence score to equal the intersection of our union between that's the IOU between the predicted box and the ground truth. So each of the bounding boxes consists of 5 predictions. That's the X, Y, W, and H. The XY coordinates represent the center of the box. That's the X center, Y center, and then the W and H represent the width and the height. This width and height is predicted relative to the whole image, so this is a very important point to note. Now for evaluating YOLO on the Pascal VOC, The others use S equals 7, B equals 2, and note that the Pascal VOC dataset has 20 classes, so C equals 20. Now the final prediction is a 7 by 7 by 30 tensor. Now this is gotten with this formula right here, where we have 7 by 7 grid cell by the number of predictions per grid cell B times 5 plus C. Now this 5 is for the X, Y that we had before. That was the X, Y, W, H, and the confidence score. So that's how we have 5. This is 1, 2, 3, 4, 5. Those 5 scores make up this 5 we have right here. And then all of this times the number of predictions. In this case, you've chosen to work with 2 predictions, and then plus C. C is actually the 20 different classes. Now, if the description from the paper wasn't very clear, we could take out this more detailed description of how the output of a YOLO model is structured. So supposing we have this image, we'll see right here. We design the output in such a way that we have this S by S by 27 tensor. Now we shall understand why we have 27 shortly. For now we have S equals 7, S equals 7 because we have the 7 by 7 grid cells. So this is why we have the 7 by 7. Now the next part, that is for each of these grid cells, we have to select one out of the number of classes we have. So in this case, for example, we have to calculate the probability of having a class given that we've said that we're going to have an object in this grid cell. Next, we have the X. The X here stands for the bounding box. That's or one of the values in the bounding box. That is the X center, the center of the object. And then the next is Y. That's the Y center of the object. The next is the width of the bounding box. The next is the height of the bounding box. And finally, we have the probability of having the object. That's a confidence score actually, which is the probability of having the object times the IOU. Now, before continuing explaining here, let's understand the concept of the IOU. Now, let's imagine we have this predictions, or we have 2 predictions. Recall that we've said that this is the output. It's true we've attached this input to this, but this is actually the output. Now, this output or this input put out like this just shows us how this input is related with the final output tensor we have. So suppose we have an output, or we have a result or a detection where we have the probability of having the object to be 1, or this probability here, which is 1. We have another output which gives us the same probability to be 1, but then for one of them we have an IOU. Now the IOU is actually a factor between 0 and 1, and it tells us how close or how similar the predicted output is with the true output. So if we have a confidence score of 1 and then an IOU, for example, of 0.1, then obviously we have a confidence score of 0.1. Or rather, if we have a probability here of 1 and an IOU of 0.1, then the confidence score is 0.1. Now, if we have a probability of 1 and an IOU of say 0.9, then the confidence score is 0.9. Now, this IOU is related to this bounding box values because it shows us how close the predicted output is with the true output, and that obviously should count in this confidence score. So let's take a look at the IOU. Let's suppose we have 2 outputs, one which produces this bounding box and another which produces this other bounding box. Now note that in the output we had the bounding box is gotten with the X, Y, W, H coordinates. So we have the center, which gives us X, Y, the W, H, the width, and the height. So if we have these 2 bounding boxes, suppose this is A and this is bounding box B. If this is the predicted and then this is the true bounding box, we have an IOU here, which is calculated with the formula intersection divided by union. So what we do is we'll find the intersection of these 2 images. So if we have this obviously we see clear that this is the intersection, which we can extrapolate and put out here. And then the union is basically taking all this, which is what we have extracted here. So taking this and dividing by this tells us how similar or how close these two bounding boxes are. Now suppose we have two other bounding boxes like this, where we have there's one in here and there's another one, where practically they are at the same position. Then in that case, the intersection will be the same as the union, hence the IOU will be equals 1. So the greater the IOU, the more or the closer the two boxes are. Now suppose we have these two boxes, we'll see clearly here that these two boxes don't actually touch each other. So there's an intersection of 0, whereas the union is the sum of this with this, or the sum of this area with this area, and that gives us a value of 0 because the intersection is 0. So in this case we have IOU 0. In this case we have a small IOU because the intersection is quite small compared to the union. So in the case where we have a probability score of 1 and with this kind of intersection, then the confidence score is reduced. Whereas if we have a probability score of 1 with this kind of intersection, then the IOU is gonna make the confidence score to be reasonable enough. So coming back to this, if we look back at this probability of having the class, given that we've set it as an object, we'll have here actually 22 classes. Now let's explain. The Pascal VOC comes with 20 classes. Then there's an additional background class. So in the case where in the case where we have no object, we could include a background class. Then apart from that, we have also the class for the gun. Recall that we had those two images which we passed through the remodeled AI platform, which generated the data set or the annotations. And so we are going to add this into this. So we are going to have not only 21, that's not only 20 plus the background, then plus the guns, that's the gun data set, making up 22. Now 22 plus the X, that's 1, 23, 24, 25, 26, 27. That's what gives us this value we have right here. And then the 7 by 7 is simply the number of grid cells. So basically what YOLO does is, for each of the grid cells, it's going to say whether there is an object. Then it's going to locate the object, and then it's going to tell us what class that object belongs to. And so comparing with the formula that was given in the paper, we have this 7 by 7 by 27 equals S by S times. Now right here we have the 5 times 1. So we've selected B to be equals 1, unlike the paper where they chose B to be 2. So here we're working with B equals 1. So that's it. We have 5 now plus 22 number of classes, and that's exactly what we expect here. Now that that's understood, let's now take a concrete example. So we'll come back to our initial example. We could see that we've actually drawn the grid cells by hand. Now suppose we have our YOLO model and we want to generate the output. So if we want to generate this output, then we'll have a 7 by 7 by 27 tensor as we've discussed. And then for each of these 49 positions, since we have 7 by 7 gives us 49 different positions, then we have to say whether there's an object or not. Say in case where there's an object, give the specific class, and then also give the bounding box values. Now let's suppose we're dealing with this grid cell, for example. Here we're gonna have a confidence of 0. So our ground truth is that we have a confidence of 0 right here. We also have random values for the bounding boxes, because when there's no confidence, or rather when there is no object, is needless talking about the bounding box. And then for the class, we're gonna select the background. So if we have 22 different classes, obviously it's a 100 vector. Then if the background is takes the first position, then we have 1, we have 0, we have 0, right up to the end. So right up to the end we have 0. So this is 22 different values and then we have 1 on the first value and the 0 for the rest, because it's basically a background. And then the confidence is 0 for the bounding box. The value is there too. We could take any value, so we'll just set all of this to 0. So that's it for this grid cell. That's how we encode this grid cell. Then for the next one, let's come and pick up this grid cell. Suppose we're in this grid cell. Now we could see clearly here that we have the center of this aeroplane, which is somewhere around this. So the center is around this position. Then it means this grid cell is responsible for detecting this aeroplane. So we have seen this in the paper, and that's exactly what it means. So this grid cell is responsible for that. It means this grid cell is not responsible, this is not responsible, this is not responsible for this aeroplane, whereas this other grid cell right here is responsible for this aeroplane. This grid cell here is responsible for this person. This grid cell is responsible for this person, and that's it. For this car, we could, if we have the center around here, we have something like this. So it's grid cell that's responsible for this one. Is a grid cell that's responsible. So that's basically it. Now let's focus on this aeroplane right here to obtain the different values as we have done for this, where we had this background. Now for this values, we shall write the values in other grid cells. So it's actually this grid cell we're working with, so we'll just write it here since it's going to be clearer up here. Now object or not, yes, there's an object, so we have a 1. We have this as a probability of having an object. Then now we move to the class. We could specify the class. So aeroplane, let's suppose it occupies the 7th position, so we have 0 for the class. So these are the classes. We're done with that. We have the 1, then the confidence, or rather the class scores, where we have 0, 0, 0, 0, 0, 0. Since this occupies the 7th position, that's aeroplane in the list of classes, we have a 1, and then the rest of the values are zeros. So here we have 22 different positions for the 22 different classes we're working with. Then once we're done with the classes, now we're left with the bounding box values. So we're left with the value for X, the value for Y, the value for W, and the value for H. Now it was said in the paper that the values for X and Y are with respect to the grid cell. So it's going to be with respect to this grid cell, and obviously the reference is this. That's the top left corner, which is this. So this is our origin for this grid cell, whereas for the width and the height is given with respect to the whole image. So that's how we work it out. Now that's said, looking at the data, that's the Pascal VOC data set right here, where we had 104, 71, 379, 180. We've seen this already, we understood this. This is the X mean, Y mean position, for example, and then if we send this way, and then this is the X max, Y max position, which we could read from this. So if I put this on this, we read this value that we had right here. So that's it. Now the YOLO doesn't actually take the X mean and Y mean. It actually works with the X center and Y center. So basically what we're saying is, since you have this X mean and Y mean, you have to compute the X center, Y center. Looking at this, to get the X center, Y center, we have 104, that's X mean, plus 379, and then divided by 2 to obtain the midpoint. And with that, if we compute that, we have 241.5. Now let us look at ourselves. Let's look at the X center now more accurately as compared to what we just did here. We move our cursor, we are at 241. This, okay, that's fine. So we are around this 241. So this is our X, and then let's now look at the Y. For Y is Y mean plus Y max divided by 2, 71 plus 180 divided by 2. That gives us 125.5. So if I go down, we have 127, 125.5 should be around this. Okay, so we see that this is the actual position for the Y, and since the X will shift this way, so this is now the center of this. So this is actually the center, it's not this one. Now once we have this we are given this value, or the way we're going to represent it in our output label is going to be such that this is with respect to this origin right here, this the origin of its own grid cell. And note that the distance from this to this point, or just the height or the width of a grid cell, is considered to be 1. So from year to year is 1, from year to year is 1. So from, suppose that this, for example, suppose that from this point to this point is 0.4, and that from this point to this is 0.2. So if we have this, for example, so we can connect that vector, then in this referential right here we have this is 0.4, and then this other one here is 0.2. So this is the points 0.4, 0.2 with respect to this particular grid. So that's the way the author prescribed that the X center and Y center be put in the output label. Now note that if you just go ahead and then put out the X center, Y center like this, like you calculate it, you have the values, the raw values, or the raw values in pixels like this, and then you want to train the model, you're going to face many difficulties in obtaining convergence, because the model is going to be very unstable. So it's also very important that after this you actually try to retrain the model on your own, so you learn how to train such models and learn techniques to train models faster, because that too counts very much. It doesn't suffice to build or to write some code which works, and then when you want to train on, say, 1 million images, it starts to trouble you. So you have to understand how this is done, and this is like one of the techniques which is used to make training go faster. Now that we've estimated this, let's now see exactly how we could calculate this automatically. So the way we could do this is, given that the midpoints, so we have our midpoint value is actually equals 241.5, 127.5. Now to obtain that value 0.4, as we actually just approximated right here, what we'll do is we're going to define a new coordinate system. So instead of the usual coordinate system where we're going from 0 to 500 and then from 0 to 281, we're going to have a coordinate system where we're going from 0 to 7, or from 0 to 6, and then from 0 to 6, since we have 7 different grid cells. So this is the first grid cell, so this is 0. Let's shift this. So this is 0, 1, 2, 3, 4, 5, 6. Then 0, 1, 2, 3, 4, 5, 6. So these grid cells now could be considered as points. And if we consider them as points, we want to convert any value we had in the previous coordinate system where we had this 500 by 281 points to a new point in the new coordinate system where we have, or to the same point but in the new coordinate system where we have values ranging from 0 to 6 and from 0 to 6. So it's a 6, or rather it's a 7 by 7 coordinate system. So to do that, like for this, for the X, we'll simply divide by the width of the image. So we divide by the width of the image right here, and then we multiply with the value of the new coordinate system, that is 7. So we multiply with the highest value in the new coordinate system. So taking this divided by this and multiply by 7, we have 3.38, which actually makes some sense because this is 1, 2, 3, like 1, 2, 3. Then this is around 0.4, so it's 0.38. 3.38, if you approximate, it gives something like 3.4. So this is 1, 2, 3, then 0.4. So we see how we leave from the previous coordinate system to this new coordinate system where we have 7 by 7 grid cells. And then for the Y, we have this divided by 281, then times 7. So we convert it into the new coordinate system, times 7. It gives us 3.176. So that's a 3.18. So this is quite similar to what we had approximated here. That's 0.2. So we have 1, 2, 3.2 or 3.18. But then we're not interested in getting this with respect to this origin, but with respect to this origin. So we have to subtract the 3's we have. So we have -3, and then this -3. It gives us now 0.38, and right here 0.18. So we have this 0.18. So let's repeat the same exercise for this person right here. Suppose we have this person, and then let's take this coordinates. We have this person at this. This is a point 22,188. So okay, yeah, this should match with this person instead. It should be this person right here. So we're dealing with this person. Let's give some space. We have this person right here. Let's calculate x center. X center will be equals this 26 plus 44 divided by 2. So let's do this way, divided by 2. For the y center, as you could see right here, we have 189 plus 238 divided by 2, 213.5. Then we go to the next step where we have to change the coordinate system. So here we have 35 divided by the maximum value of the previous coordinate system times the new coordinate system, and that gives us 0.49. Then for the y center, the same, it gives us 5.318. Now this 0.49 gives us an x center of 0.49 still, and this y center gives us 5.318 minus 5. So it gives us 0.318. It tells us that based on this origin, we're practically at the center, and then we are at almost 1/3 or around 1/3 of the y. So we are on this. So if we do this, we see that we fall around this point right here based on this origin, actually the origin of this grid cell. And then obviously we have the class labels, which we know already. For the when we get to the point where with a person we put 1 and the rest is zeros, the probability of having an object is 1. So that's how we encode, or that's how we create our output labels or our output tensors. Now note that if the grid size changes, that's if we leave from say 7x7 to 13x13, then we're not going to have any problem, because basically we just have to modify this and just have 13, and right here 13. Then the next part now is to encode the width and the height. Now obviously from this we could calculate the width and the height, but then the width and the height is divided by the overall width and the overall height respectively. So like this, for example, to get the width here, let's take this off. To obtain the width, we have the x max minus x mean simply, and then to obtain the height, we have y max minus y mean. Now the new width, let's use some Python notation. The new width is this. So we have the width equals the width now divided by 500, and then the height is this divided by 281. So that's basically what we get. And in this case, for example, we could do the calculation very quickly. We have x max minus x mean, 44 minus 26. We have here 18, this 49, this dividing by 500, 18 divided by 500 gives us 0.036. And then for the height, we have 49 divided by 281 gives us 0.17. So we see that basically what we're doing is that we're normalizing or standardizing all this bounding box values. Now once this is done, we could get into design. Here the implemented model as a convolutional neural network and evaluate it on the Pascal VOC. The initial conv layers of the network extract features from the image, while the fully connected layers predict the output probabilities and the coordinates. So this architecture is inspired by the Google net model that's the inception net for image classification. So to define this, and then we have this actually, where they have 24 conv layers followed by 2 fully connected layers, and they alternate the 1 by 1 conv layers to reduce the feature space from preceding layers. Then they pre-train the conv layers on the image net classification tags. This is very important because with the pre-trained network, we are able to extract very relevant features from the images, and to make it easier for us now to train the model, or to train all this conv net to do more specific tasks, like, or to learn more specific tasks now, like the classification and then the object localization. So that's it. We have to pre-train, and here we have all the necessary details. Nonetheless, we are not going to use this. We're going to use a very light model. We're going to use the mobile net. So our backbone is going to be a mobile net. We're going to stack up some convolutional layers, a fully connected layer, and then we shall reshape our output, and it will look somehow like this, but not exactly the same, because we're going to be using a completely different backbone, and then there shall be some difference in this. But the main idea with what we're going to be doing is that we're going to be trying to build an object detection system for low resource environments. Now let's go ahead to define our model for the task. Right here we have the input dimension, which we define as 224, number of filters to be 16, we shall see it shortly. The split size S, which we know already. The number of classes we are dealing with. We have the number of predictions per box. So number of predictions per box, which is this, is 1. The output dimension, which is S by S, 7 by 7 by 27. The output shape, 7 by 7 by 27. Now this is 7 times 7 times 27 actually. Now the input, we define the TensorFlow that Keras input. We have a base model, which is the mobile net. So unlike the base model used in the paper, we're going to use a much lighter model, which is the mobile net, which has already been trained on ImageNet, so no need for us to retrain it again. Now we freeze the base model, and then we actually now add 3 convolutional layers. Now the number of filters here has been defined already as 16. For the first we have 16, the next is 8, the next is the output dimension. So in this case we have 7 by 7 by 27. We have layer normalization. We actually tried batch normalization, but it happened that layer normalization, the model actually trained faster. Now with the global average pooling, then the dense layer, and then reshape. So with this, we run this, and there we go. Now before looking at that, note that we have the kernel initializers with a random normal initializer, which is also very important as it permits us train faster. Activation ReLU everywhere. We do not use the leaky ReLU, although you may modify this and use a leaky ReLU instead. So looking at this, we have our input after the mobile net. We have this, we have the conv layer and the conv layer, this other conv layer, this number of outputs, the layer normalization, the global average pooling, the dense layer, and then the reshape. So it takes up the shape we are actually wanting to work with. So in that sense, if we have a split size, so suppose we have a split size of say 13, you see this gets modified automatically. So we have 13 by 13 by 27. So let's come back to this. We have the split size of 7, and this is what we get.